This video is going to show you how to do problem 22 out of chapter 10. So let's read through the problem. Although your product, some word game, has a list price of $12.95, each store is free to set prices as it wishes. Your marketing department believes that the games generally sell at a mean discount rate of about 12% from the list price. You've just completed a quick survey and determined the prices at some stores. So let's start by identifying the null and alternative. I'm going to go over to Word here and do that. So let mu equal the true mean selling price of our game. Now we need to state the null and alternative. The null is that mu is equal to $12.95 times 88%. So if we take 12% off list, that means that it's selling at 88% of the list price, and that was $11.40. The alternative is that mu then does not equal $11.40, 39.6 cents. Let's go back to the course packet. So we've identified the null and alternative hypothesis. Now we have to find the mean. We have to find, so approximately how different is the selling price from the average. What they're asking for there is the standard error. Then we need a 95% confidence interval. We need to test the hypothesis. So the absolute first thing that we should do is look at the data, and we see there's only a pretty small handful of values, maybe only a dozen values. Whenever we see that, we get nervous about normality. So we can't use a t-test unless the underlying population distribution is at least fairly normal. We're very worried about outliers and skewness with such a dinky sample. So we need normality. If I go over to Firefox, not Firefox, Firefox has the Google site loaded up. Here's that data set. So let's download word.sav. We'll save it, and then I'll just double click on it to bring it up in SPSS. And let's go see if we can find it here. Okay, eventually it comes up. So the first thing that we want to do is look at our data. And the best place to look at your data for a single sample situation like this is to go up to Descriptives, and then we're going to go to Explore. Let's bring price in and go over to plots for a second. Let's get a histogram as well as a box plot. If we go look at our course packet, they're after a 95% confidence interval. So remember, Explore by default gives you 95%. If you want to check that, go into stats and you'll see, sure enough, you get a 95% confidence interval. So we don't need to change anything there. So we're all set to hit OK. And let's start out with the box plot. And the first thing that we see is that there's an outlier. So there's some store that presumably is selling it for 90 some cents, or under a dollar, and it seems to be observation 3. So let's go look at that. And sure enough, there's a 0.90 there. Actually, it's 0.895. If we go over to the course packet, you're going to notice that there's a typo. So I had typed that data set in last year when I taught this for the evening class, and it looks like I put the decimal place in the wrong place. So let's just change the decimal place, and so now it's 895. So this is and I hadn't intended to do this, but I think I'm going to leave it this way just because it's a great lesson to look at your data. So now that I've fixed the outlier, let's go rerun everything. So we'll just go back to Explore, go hit OK. And we should look at our box plot, examine it for normality. We have a really small sample size, and the box plot looks rather strange. So here's your median. So half the data are at about $10 or less. The other half sit up here. So it's a really odd distribution. I'm curious to see what the histogram looks like. And the histogram reveals that we almost have two segments. It looks like there's a segment of stores, so it's a bimodal distribution. You've got a segment of stores that sell your game for list price, and then you've got another segment of stores, probably some discounters, that discount it for probably $9.95. You get a couple that are even, you get that one that's even cheaper for $8.95 that shows up down there. So you really have two modes there. I'm going to proceed cautiously at this point. Perhaps the mean isn't the greatest summary, since we've got a bimodal distribution, and it's like we've got two types of stores is what the data's saying. But if we wanted to do a test for the mean, I'm going to proceed cautiously. We need a normal distribution. We don't really have one. However, the distribution is not horribly skewed, and we're going to see in a couple weeks that if you have a distribution that's flat, the CLT converges fairly quickly. So let's proceed, and if the p-value is not close, then we'll go with whatever the p-value tells us, or the confidence level. If it's on the border, then I'm going to be pretty nervous about it. So our confidence interval is 1187. Let's go write that down. So the confidence interval is 987 through the upper bound is $12.25. And we note that the reference value is in that confidence interval, so we cannot reject mu equal to $11.40-ish. So that's definitely a possibility. Now we could also do this with a t-test. So let's go up to Analyze, Compare Means, and we're going to use a one-sample t-test. I'll copy price in, and then the other thing that students very often forget to do is to set the test value. So $11.396 is the test value. Go hit OK. And here's what you get. The p-value is 0.538. So let's go back to Word. We could also say p is equal to 0.538, which is greater than 5%. So we cannot reject H0. $11.39.6 is a possible mean. So we can't rule that out. The only other thing that would be useful, I think, is for us to discuss where that number comes from. So I'm going to go over to the scratch pad for a second, and let's clear it off. And let's draw the situation. So here's the distribution of x bar. Under the null hypothesis, we're going to make the mean $11.40. Let's just round it. And we've gone off and drawn a sample of 10 stores and found a mean of $11.06. So $11.06 must be about here. And what we need to do is evaluate the area in that tail. So we need to find the probability that x bar is less than 11.06. Now, this is going to be exactly equal to the chance that I have a t statistic less than 11.06 minus the mean, which is $11.40-ish, divide by the standard error. Well, let's go get our standard error. So the standard error is given to us right here, 0.5273. So 0.5273. I like to write my standard error next to the distribution. So that's our best estimate of the standard deviation of that distribution. Now, this ratio is so important that SPSS and just about every stats package on Earth reports it. So that's called a t statistic, and it's minus 0.641, indicating that 11.06 is about 0.6 of a standard deviation to the left of the mean of that distribution. So that's what that value tells us. Now the p-value indicates the area of both tails, so it's 0.538. I'm going to go draw this in. 0.538 over 2 gives us the area of one of those tails. The area of the other tail is also 0.538 over 2, so that when you combine them, you get 0.538. So we could write that this is just 0.538 divided by 2. So I like knowing what all the numbers in the output tell me. The mean difference is the difference between the sample mean and the test value. So this is saying that the value we've observed from our sample of 10 is about 34 cents less than the test value. If you wanted a confidence interval for that difference, here it is. Notice that 0 is in that interval, indicating again that you cannot reject H0. So in real life, what you would do in this problem is you would first, fix your outlier as we did. Here you would say, well, let's proceed cautiously. Even though you've got two segments of stores, we can still talk about a mean, although the mean may not be the most useful description. So, what I think probably a better way to characterize this is you've got two types of stores, full price and discount, and the typical discount store is down here around $9 to $10. But we can still talk about the mean overall, and we cannot reject the null hypothesis that the overall mean is about $11.40. You just go to your p-value to conclude that, or use your confidence interval.